We can apply these ideas to a simple problem in wave superposition. And let's take a look at this simple example. I'm given two waves, electric fields, 4 probably volts per meter, 3 volts per meter, and then by the time I've computed their distances and their wavelengths, I get that alpha 1 is 30 degrees and alpha 2 was 60 degrees in terms of the angular portion. And you're asked to write or find the superposition, so you want to find E in this form here. And again, I just identified alpha 1 is 30 degrees, alpha 2 is 60 degrees. So delta, I take alpha 2 minus alpha 1, 60 minus 30, which is 30. Um, Here I like the vector method, so let me do the vector method. I get the x and y components of the sum. So the first wave has x component a1 cosine alpha 1. Second wave has the x component a2 cosine alpha 2. Plug in the values. A1 is 4, A2 is 3. So this simply becomes 4 cosine 30 degrees plus 3 cosine 60 degrees, alpha 1 and alpha 2. And when I computed those, I get this. And then just add those together to get 4.964. Likewise for the y component, of those vectors are a1 sine alpha 1, a2 sine alpha 2, just getting the y component. Alpha 1 30, alpha 2 60, a1 4 and 3, and when I compute those, I get this. And then just do the sum. So the amplitude is the square root of the sum of all these. If there was more, I could have added another wave or 2 or 3 or 4 and added all of their components. But the total x component of the resultant is sx squared and sy squared. And here I've got 4.964, 4.598. And when I computed that, I got 6.77. So the resultant amplitude 6.77. And then once I have the components, so the resultant, I can get the angle theta, Sy over Sx, which is 4.598, this value, 4.964, this value here. Ratio of those, it comes out that the tangent is 0.926, and then when I use my calculator, that turned out to be 42.8 degrees, basically. So I could write in totally consistent form that the resultant electric field would be 6.77 volts per meter times the sine of 42.81 plus or minus omega t.